talked about this. Here it is. This area optimization sort of problem, right? Farmer Ed building a barn. I don't know where I actually did that. Probably on a different sheet. Yeah, there we go. What we need to do is identify what we're actually building, right? So get a what constraints or what restrictions we're working under. Here you're trying to build these two sides and that side. It's a rectangle. We're always only going to be working with rectangles for like our context, because to do anything more complicated than that, you pretty much need some calculus techniques that we don't have yet. So dealing with rectangles, things that run the same direction are the same length, so I labeled them the same, right? These are x's. This is something else, right? I can't call it x, because if I call it x, then I'm saying it's the same as the other sides, and it probably isn't, or at least might not be. So call it something else. Then we do this substitution into an expression for area, which is the length times width. End up with a quadratic, looking for the maximum, so we find the vertex. I asked you to go home and do this one. I don't remember if we did, any of the sort of setup stuff together, but we have a rectangle. Yeah, I think we at least drew a picture, right? Okay. We've got something like that. We need to label it. And the idea is that since this is a rectangle, those are all the same length, so call it something, X or L or W or whatever you want to call it. And then those are a different something. Well, Y maybe. Y is this whole distance across. Okay, so then what does the constraint or the perimeter, and again, maybe perimeter kind of in scare quotes, we don't really mean the distance just around the outside, but all of the stuff that we're building. Okay. I don't think I did anything, but I know, right? Yeah, I think maybe it's when I step on this conduit thing with the. Already thought about it. Think about how you would set up that constraint or perimeter equation. Okay, there we go. We're back. Okay. We got 450 feet of fence to use. And out of that 450, we need to build what? 3 X's and 2 Y's, the way I've got it labeled. Okay, let's go ahead and solve that either for X or for Y. Which one do you want to look for or go for? Y. Okay. Doesn't matter, just pick one. If one of these had, no coefficient or coefficient 1, that's all for that one. Here, it's going to be about the same either way. So basis says Y, let's solve for Y. So I'm going to subtract 3X from both sides. So 2Y is 450 minus 3X, and then divide by 2. Y is 225 minus 3 halves X. Okay. What's the area then? Okay. Area is X times Y, but we can plug that in or substitute that in place of Y. Oh, that's a 2, not a 3. There we go. To get something like that, I'm going to go ahead and expand, like distribute that. And I'm going to rearrange at the same time. So, hope that's okay. What are we trying to find? The vertex, the maximum, This is quadratic and opening down, so the maximum is going to occur at the vertex then. The x coordinate, and I wrote this in terms of x, so the x coordinate of the vertex is negative b over 2a. Punch that all into a calculator, do the arithmetic, what do you get? 75. That's a 7. Yeah, kind of weird on me. All right, so x is 75. Probably a good idea to go back to the question, what dimensions will maximize the enclosed area? So dimensions would be what are the length and the width. We've got one of them. What's the other one then? If x is 75, what's y? How'd you find it? Okay, you can go right there and plug it in because we already figured out how to, like, we made an equation for y in terms of x, right? So you can go right there and plug 75 in. You could go back here and plug 75 in. You could just think about what we're dealing with. We had 450 feet of fence and we used 75 and then another 75 and then another 75. So what's left over? 450 minus 75 three times, which is 225. And you need to build these two sides out of it, so cut it in half, right? So lots of ways to do that. Don't think of that part as like a formulaic, you got to go here and plug in thing. Just, there are lots of places that you can take this and find this. Those would be the dimensions then. 75 by 112.5. I don't care what order you list dimensions in if it's something I'm grading. The homework, because it's a computer grading it, probably is going to ask you to, if it asks for dimensions at all, I didn't look closely enough at what the question asked for to know, but it might ask you for like, what's the longer side or what's the shorter side or something like that, right? Because it might care about the order because computers are stupid and that's what's grading it, right? The maximum area is just 75 times 112.5, which is something. Again, but like 100 times louder, I know. Okay. That'd be the maximum area then.
Just knowing that I get stuck on the area part for the x equals y, because when I was doing the homework, it was just beating me up, so I just gave up and
Okay.
waited for today. Is there any, 'cause I couldn't figure out how to get the square part. That was what I kept struggling, like, how do I know what to multiply by?
Okay, so you okay with how we set this up?
Yeah.
Okay, and why the area is x times y? Okay, right, yeah. Okay, so once we've got this tells us how x and y are related to each other with the, situation that we're dealing with, the amount of material that we've got. To make this into something we can actually use and deal with, I need to reduce the number of things I don't know. So what we do is use this piece of information to figure out how to write one of the things in terms of the other one. So here we solve for y. You could just as easily have solved it for x and you'd get to the same place. We would have found this first and then this, but we get to the same place. Same answer, doesn't change anything about how we do it. So solve for one of them and then substitute it in here. Yeah. So you just replace the thing you solved for with what you learned about it. And then you end up with a square and then you can find the vertex. Okay. Everybody good with that? Okay. All right. Okay. So we've talked about quadratic functions and kind of, we've figured out all the stuff we can figure out about quadratic functions. You know what? I'm not going to write it because it's all written down here somewhere. We know how to deal with these two different forms of writing a quadratic. Hopefully we're comfortable moving back and forth between them. If you have one and want the other, to go this way, you just sort of expand and collect terms. To go this way, you complete the square, but we can move back and forth between them. With either one, we can find the vertex. Here, it's just kind of sitting there because, we're thinking of like transformations and read it off. The standard form thing, the vertex, got that negative b over 2a, little formula thing to figure out where it is. I guess the other piece of information that we probably want to think about when we see quadratics come up in places is, does this open up and have a minimum, or does it open down and have a max? Right, and that's based on whether that leading term is positive or negative. So what we're going to talk about today is solving equations involving some kind of quadratic. And there's a whole bunch of problems here that we'll have time to work on, but I'm going to start by doing a little bit of factoring review first. This is one of those things that is, a prerequisite. Like, this coming in, but I know that, what that means is not always the same for everybody. So let's just talk about it for a minute. Things to look for. We're just going to do this as like some examples. If we want to factor that, what can we do? Yeah. They have a common factor of x. If I take x out, what's left? 3x plus 4. Okay, so on the, factoring flow chart of things to look for. First thing to look for is, are there any common factors that we can take out? If there are common factors, start there. What would be a common factor for twelve x to the seventh plus 4x cubed plus 2x squared? They're all even, so we can take 2 out. And 2 is the biggest thing we can take out, right? If we're going to like stick with whole numbers. If I wanted to get weird with it, I could take 12 out and then these become fractions, but I don't, right? Just take the biggest like whole number part. X to the seventh, x cubed, and x squared. What do those have in common? X, how many of them? 2, right? Seventh means 7 copies. Third means 3 copies. Squared means 2 copies, so I can take 2 out. What's left behind when we take out 2x squared? 6, x to the fifth. There were 7 and we took away 2. Plus 2x plus 1, right? Something to hold the place. Factoring, good thing about factoring is that it's easy to check to see if we did it right. Just undo it, right? I should be able to distribute this back through and get back the thing I started with, which is why we need this here to sort of hold the place for that term, right? You took 2x squared. I mean, really what we're doing is dividing. If you divide 2x squared by 2x squared, what's left is 1. Everybody feel good about that? Okay, good. Now, another like factoring tool that we have would be completing the square, right? And it's maybe not the first thing we're going to like reach for if we're trying to factor a thing, but that's a type of factoring. We've already kind of done that to death this week. What if I want to factor something like x squared plus 5x plus 6? A trinomial, it's got 3 terms with nothing common to all 3, right? These 2 have x's in them, this one doesn't. These 2 have, numeric coefficients, this one doesn't. I mean, it does, but it's 1. there's nothing common all the way across here. So no common factors. What do we go to then? If it's a square, then if it factors, there's some way to write it as a product of linear things, right? Degree 1 things. If the leading term is x squared, then those linear factors will look something like that, right? Okay, now we're not trying to force it to be a perfect square, so we're not completing the square because we're kind of going to a different place. I'll talk more about that in a minute. We're just trying to factor what's already there. So think about how the expansion would go. First part hits the first part here, and you get x squared. The product of the outer terms, so x times something here, and the inner terms, x times something here, adds up to 5x. So whatever these two things are that are, missing at the moment, those need to add to 5. And then the last part of the product, when these things hit each other, gives 6. So we're looking for a pair of numbers that add to 5 and multiply to 6. Two and three. Add to 5, multiply to 6. 2 and 3. All right. I'm going to throw in a step here in the middle that, maybe we don't always write, but what I'm doing then is splitting that middle term up into 2x and 3x, right? And then thinking of this as the result of expanding a thing. All right, now if it works, we should be able to work back up and get the same thing. So let's check. Expanding this, x times x is x squared. X times 3 is plus 3x. Okay, so I've got my outer and inner backwards, but that's okay. Fuel works just as well as flow, right? So 3x plus 2x, and then 2 times 3 plus 6. If you have a different way to factor things, like I know there's some kind of thing where people draw like an X thing and put things in like these. Well, I don't know how that one works. Or like a box kind of thing. If this is x squared, then this is x and this is x. So our factors are going to end up, sort of along the top and the bottom here. This is x times 2. This is x times 3. And then 3 times 2 is 6. Like whatever you have for factoring is fine. I don't care how you do it as long as you can. Is this familiar? Is anybody like totally in the woods? Okay. All right. So factoring is it's kind of making an educated guess, right? And just being a little clever about it, about how the thing's going to work out. The educated guess part is that we want to look for a pair of numbers that multiply to whatever a times c is, which here would be 7. And add to b, which is 8. So can we find a way to factor 7? Well, what are factors of 7? 7's prime, so 7 and 1. That's it, right? So either positive 7 and positive 1 or negative 7 and negative 1. Those are the only choices that are going to be nice, and we only care about factoring, nice stuff. So can I take a pair of factors of 7 that add to 8? Yeah. 7 plus 1 is 8. That means this factors into x plus 7 and x plus 1. And then again, I can check x times x is x squared, 1x plus 7x, and then 7 times 1. Can we always factor? No. What if this had been x squared plus, I don't know, 4x plus 7? I'd still be looking for things that multiply to 7, but now they add to 4. Can I find factors of 7 that add to 4? No, because the only factors of 7 are 1 and 7. That means that's not going to factor. That means that, that's the end of that, road. I go do something else. So factoring doesn't always work. We pretty much want to be comfortable enough with the idea that we can kind of quickly check to see if something is going to factor, if something that factors easily is going to factor, right? So again, maybe this takes a little bit of practice to build up to this, but these two are examples of things that factor pretty easily. As long as we kind of understand what's going on, you need to find a pair of numbers that multiply to give you C, or A times C, and add to give you B. Okay, well, here's 1, C is 7, so multiply to 7, adds to 8. There you go, 1 and 7. We factor it, we check real quick, we're good to go, we move on. If something doesn't factor, or if something is like really giving me fits, does that factor? Can I find numbers that multiply to 60? Okay, factors of 60, there are a ton of factors of 60. 1 and 60, 2 and 30, 3 and 20, like on and on and on. There are a bunch of them. I need to find a pair that add to 19. Okay, 4 and 15 work. It does factor. But we're going to be like perfectly within our rights to look at something like this and say, no, I'm not going to worry about trying to factor that, right? So factoring is never going to be our only option. But when it does work for the, again, like kind of straightforward cases like this, it's a good, quick, easy way to sort of do the thing. Okay. So if you feel a little rusty on factoring, work on it a little bit, but don't stress about it too much because it's never going to be the only tool we have. Okay. Solving quadratic equations. Let's say we wanted to solve, and this isn't in the notes, this is a different one. I want you to be able to enjoy those. Let's say we want to solve that. X plus 1 squared, x plus 1 all squared, minus 16 equals 0. Take just a couple of minutes and, think. Look for things we might be able to do there. Anybody have an idea they want to share? Okay. So go ahead and expand that. Okay. That's x plus 1 times itself. So x squared plus 2x plus 1 minus 16 equals 0 still. Now, that set of parentheses isn't really doing anything anymore because we squared, right? So combine like terms, x squared plus 2x minus 15 equals 0. All right, we've expanded, we've collected like terms. Now what? Okay, can we factor? We need to find a pair of numbers that multiply to negative 15 and add to factors of 15. 1 and 15 are too far apart, right? 3 and 5. And then we just need to make sure we get the signs right. This is negative, so it's one of each. Positive 2, so plus 5 and minus 3. Okay, so I think this factors as x plus 5 times x minus 3. Check, though. X squared plus 5x minus 3x. 5 minus 3, so plus 2x. And then minus 15 for the constant term, the last part. Okay, so that is how that factors. Well, what did that do for us? Oh, could we?
It 15 squared it, then subtracted 1.
Okay, let's come back to that in a second. Yeah, yes, you can. We'll come back to that in a second. Since we've already done all this factoring stuff, let's see if we can get anywhere with it. What do we have now? And maybe don't worry about the details too much just yet. What's this? These things connected? Multiplication. Okay, so a thing times another thing, and it's equal to what? Okay, if you multiply two things and get 0, what do you know? That one of them has to be 0. The only way to multiply stuff together and get 0 is if 0 was in there somewhere to begin with, right? Okay, so that's called the zero product property. Which says that, again, what we just said, if you multiply things together and get 0, something had to be 0 in there. So, if A times B equals 0, then either A is 0 or B is 0. And the same thing's true whether you have two factors like we do here or a million of them. If you multiply things together and get 0, one of them had to be 0. So this part was very important then. If you multiply two things together and get 6, you don't know anything at all about anything, right? They could be positive, they could be negative, they could be nice, pleasant factors of 6, like 1 and 6, or they could be weird fraction things, or irrational numbers, like they could be anything. It's only 0 that has this special property. That's why it's in the name. So I'm gonna be really obnoxious in talking about, no comments, about talking about this when it comes up and really hammering on the 0 part. And I think it's probably a good idea if you do the same, at least for a while, as a reminder and to reinforce the fact that this only works because it's equal to 0. Okay? Because it never fails that, we'll get to the test and somebody will, have something like that and do what we're about to do. Okay, zero product property says if you multiply two things, you get 0. That means that either that's equal to 0, or that's equal to 0. Right? Okay. Now we, take back the curtain. If x plus 5 is 0, what's x? And if x minus 3 is 0, what's x? There are your solutions to the equation then. Why we get two of them? What did we start with? A quadratic, right? What do quadratics look like? Parabola. We're asking where it equals something. That means we're giving a y value and finding the x's that go with it. So there aren't always two answers, but often there are two answers because there are two places where, it goes through a given like height or level. So we kind of go into it expecting to probably find two. Sometimes it's less. We'll see how that works. But okay, so what did we do? We expanded everything. We factored. Because we had a factored thing equal to 0, we could apply this 0 product thing. Again, if this had been, a factored thing equal to 6 or something, that doesn't work the same way. I can't do that because this is a special property of 0. But when we split them up, then what's left is pretty straightforward. We're just solving little linear equations. Subtract 5 from both sides, add 3 to both sides. Okay, so that's one way we can do this. That's solving by factoring and the 0 product property. Nice thing about this is that once we have it factored, the solving part is almost for free, right? You split them up, you solve, but they're super, straightforward little things to solve. Bad part, or part that's maybe less helpful, is that I have to be able to factor it. We can't factor everything. Sometimes even when we can factor things, the factoring might not be easy. So this requires factoring, which, maybe isn't my favorite thing. So works sometimes. When it does work, it's nice and straightforward, which is great, but it doesn't work every time. Everybody good with that? Okay. Take 2. All right. Thomas, you said you moved 16 over? Okay. Add 16 to both sides. Add 16 to both sides so that we can get the square thing by itself? Okay. So isolate that, solve for it. Okay. Then what? Yeah. The outermost thing here is the square. So if I'm trying to solve, I'm trying to sort of peel layers away and get to x, right? The unknown. To get rid of that, I would take a square root. Which means I take the square root on both sides. On the right, we're taking the square, or sorry, that one left. We're taking the square root of a square, so what happens? They undo each other, right? We just get x plus 1. On the right-hand side is where we have to be a little bit careful. Square root of 16 is 4. But the actual statement, and maybe I should, leave an extra line in here so I can point at it. Was that x plus 1 squared, whatever it is 16. Now, when you square 4, you get 16. But you also get 16 when you square -4. So when we do this to keep track of that, really what happens over here is that when you take the square root of a square, you get the absolute value of the thing because square roots and negatives get weird, right? So to fix that, to make that work, it's technically the absolute value of the inside, the x plus 1. To correct for that, what we do is
when we take a square root, tack on a plus or minus. Because I don't know if it came from the positive or the principal square root of 16, which is 4, or the negative one, which also gives you 16 when you square it. So x plus 1 then is either positive 4 or negative 4. If it's 4, then x is 3. If it's negative 4, then x is negative 5, which is what we got the first time we worked through it. This is sometimes called the square root property. That we pick up this plus or minus along with the square root when we decide to take a square root, right? The square root itself, like if you type in a square root on your calculator, it just gives you the positive one, right? Because that's how the square root function works. We're doing the opposite or the inverse to the square. Quadratics are not one-to-one. So when we talk about their inverse or their opposite and flip things over on their side, that's not a function, right? The square root function, pew, looks like that, right? The positive part. What we have to do is sort of manually correct for the negative option, right? The thing that would be the bottom half of the sideways parabola. This is us manually correcting for the fact that it gets kind of forgotten about when you invert or go backwards. That kind of make sense? So this plus or minus, that's a thing that I have to like actively put in there, right? And do to keep track of that. Okay. Again, we get to the same solutions. Pros and cons. Well, I got to remember this thing. Anytime I got to remember a thing, that's kind of a bummer, right? So there's that. Apart from that, this is like fairly straightforward. I mean, I know, the first time is maybe different than when you've done a few on your own, but provided I keep track of that, this isn't really that bad. The problem is that this works for things that look kind of like this, right? Where I've got a like perfect square factor in there somewhere, where it makes sense to take the square root. It doesn't make any sense to try to take the square root of something that looks like this, because the square root of this isn't going to do anything useful, right? It's not going to take care of that. The rest of this is going to be a train wreck. It doesn't help with something that's in like standard form like this. Now we know a way to force stuff to go into standard form. You complete the square and you make it look like that. But that feels like going the long way, right? Like, okay, take this thing, go complete the square. That's kind of a whole thing, right? Then come back and do this. That's kind of the long way to do it. Now it always works. So you're welcome to do that. That's fine. But again, it's maybe more work than we strictly need. So we've got one way of doing things that doesn't work every time. We've got another way of doing things that does work every time. It's got a like an asterisk by because I got to remember a thing. To make it work in general, I got to maybe go out of my way and do some extra like side work stuff that is going to be maybe not the most fun thing. Thankfully, though, that extra side work stuff is not so bad that you can't just sort of call the thing A, B, and C and do it that way. And if you call the thing A, B, and C and do it that way, we get and complete the square and take the square root and all that stuff. We get a generic formula for things called the quadratic formula. Where if we have a quadratic in standard form equal to 0, that part's important because the way you derive it is to complete the square using A, B, and C, and then do the square root thing and solve for x. So if we have x squared plus bx plus c equals 0, then x is equal to, does anybody know it and like want to sing or something? I mean, I think there are different versions of songs, but I'm not gonna sing it, but I like to read it to Pop Goes the Weasel in my head. Negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm not gonna sing it because I'm recording this one, and one of my friends who I don't know, but like he just watches all my YouTube videos. He just like puts them on in the background. What's up, Braden? Oh, did he? Okay. Anyway, that's it. Negative b, so the opposite of whatever b is, plus or minus. This is the same plus or minus that happened a minute ago when we took the square root. So for the same reason, that means there are really two things here. One where you add, one where you subtract. The square root of b squared minus 4ac all over 2a. So this works every time. It's kind of always a medium amount of headache because there's a bunch of arithmetic to do, right? The formula is kind of messy. But you take your standard form equation or you put it in standard form if it's not already, you pull A, B, and C out, you mush them into this formula, you do a bunch of arithmetic stuff, and ta-da, you get answers, right? So perks, well, it works the same. It works every time. It works the same way every time. Cons, again, I got to remember a thing, right? The formula is kind of a mess. And it's always going to be, sort of a medium amount of, 5 or 6 steps of kind of cleaning things up, right? But let's see how it works. On that same example, we already did the work to put it in standard form right here. So that's this. What are A, B, and C? A equals 1, B equals 2, C equals negative 15. Sign goes along with them. So this is positive 1, positive 2, negative 15 if you need the extra reminder. Then X equals negative B, or the opposite of B if you want to read it that way. Big old square root, B squared minus 4 times A times C all over 2A. Okay. That's it. Now we're just going to clean things up a little. 2 times 1 is 2. Plus or minus, I got to start inside the square root. 2 squared. And notice, by the way, when I wrote this down, I used lots of parentheses where I'm plugging things in. That's to help us keep track of things like negatives and, when they should go away and stuff, right? I'm subtracting a negative here. This is going to end up being adding. If B had been negative, I'm squaring it anyway, so it goes away, right? 2 squared. And negative 4 times 1 times negative 15. Plus 60. So 64, the square root of which is 8. So negative 2 plus or minus 8 over 2. Now, once we've got things kind of at this point sort of cleaned up as much as they can before I need to look at that plus or minus, probably a good idea to go ahead and separate them out. So that plus or minus means 1 add and 2 subtract, right? So there's actually 2 things going on there. And then work on those separately. Negative 2 plus 8 is negative 6. Negative 2 minus 8 is negative 10. And so we get, oh, wait, no, sorry. Negative 2 plus 8 is 6, not negative 6. So we get 3 and negative 5. Same answers we got before, right? That's good news. It means this works just as well as anything else did. This is what I mean, though, about it's always kind of a medium amount of like headache. Like anytime you do a quadratic formula thing, it's going to look like this. And it's going to be about that amount of work, right? Yeah, it has to be equal to 0 before you apply the formula. So if it wasn't, then the first step would be to rearrange so that it is. Yeah. Yeah, so you might have to do a little bit of stuff beforehand to sort of get things in place. But then it's just, to take all the stuff, mash it into the formula, and then work through all this stuff. Okay. So that's 3, methods for solving quadratics. What we need to be working on then is just getting to a point where we're comfortable with that. And the thing to do is just kind of do a quick assessment, right? And think through how we might want to approach a thing. If I see something like this in there, where there's a perfect square term, I'm probably going to try to solve for that, get that by itself, so that I can take a square root and then, jump into to dealing with the solution. If it's something like this, I'm going to take about 30 seconds and think about whether I can factor that or not. So can I find two numbers that multiply to -4 and add to -2? I think for a minute, maybe I try some stuff and do some scratch work. If the answer is yes, cool, then factor it. If the answer is no, then go to the quadratic formula, right? But don't sit there for 10 minutes like beating your head against the wall trying to figure out how to factor a thing that might not factor anyway. Or if I just don't feel like it, right? Or if I look at the thing and I'm like, you know what, I don't really know what to do with that. I'm just gonna, brute force it and go with the quadratic formula. Or if you just want to use the quadratic formula every time. Like if you do this, 20 times, then this kind of medium amount of headache stuff is just going to start to, go pretty quick and not really be that big a deal. Okay. So between now and tomorrow, try a few of these. Let's say at the very least, work through a couple. We'll talk about inequalities, and I'm just going to say do at least half of these. We'll take the first, half a class or so to talk about that and talk about what inequalities look like, and then we'll talk a little bit about what happens when weird things come up here. Yeah, that's it. Y'all have a good day. I'll see you tomorrow. Office hours today, well, before class, or now 12 to 12:30. Yep. Or first thing tomorrow.